First part is analysis on manifolds. And firstly, we have smooth structures. So this would be the first section in our studies of geometry. And let's go ahead and try to solve some easier exercises in this context. Okay, we are studying two smooth structures. On the Euclidean line, and these are the ones given by atlases, so R and IDR. So this is one atlas, so one smooth atlas, and another is R and phi. So, and what is phi here? Phi is a function that is given by phi of x is x to the power of 3. Okay, so first of all, why is phi so a chart on R? Before we even start writing down any tasks of this exercise.
It covers the entire, it covers R.
Okay. Do we need any additional any additional assumptions on this phi?
It's homeomorphism.
Exactly. So it's a smooth function. It's a continuous function with a continuous inverse, right? Its continuous inverse is nothing else but the cubic root function, right? So we have to keep in mind that here we are endowing our manifold with the standard topology. Okay, so this is something that is implicit here, right? So as Grega said, phi is a homeomorphism, which means a continuous function with a continuous inverse. Okay, so the first question is, are these atlases compatible? And the second question is, are the two manifolds endowed with above atlases diffeomorphic? So let's try to solve A. What does it mean even for two atlases to be compatible?
Maybe that they have a transition map between the two of them.
Okay, yeah, it certainly, I mean, this is not a very precise way of saying it, because transition maps are defined with respect to charts, right? So,
Their union is again a smooth atlas.
sorry?
Their union is again a smooth atlas.
Yes. So, this is the definition, right? Two atlases are compatible. So, and of course, we have in mind smooth atlases. Compatible if their union is again a smooth atlas. Okay, so, and what is like the central theme of smooth atlases? What is the central definitive quality of smooth atlases?
Diffeomorphic transition maps.
Yes, exactly. So this is what we are concerned about. We are concerned about whether the transition maps are indeed, so transition maps are maps from Euclidean spaces to Euclidean spaces, right? And we are concerned whether these are diffeomorphisms in the usual sense, right? So in the sense of your favorite analysis course, or for physicists, it's Mathematica 3. Okay, so let's try to maybe draw something. Okay, first of all, we have like this R here that is the abstract manifold. Okay, the abstract manifold in question. Okay, and then we have these two charts. One is IDR, and the second one is phi. So
I have a question.
yeah,
How does the union of two atlases look like?
the union of two families of sets.
Wouldn't that mean that every open set has two images?
Sorry, I'm not sure I understand.
Because if an atlas is like for every open set U, we map it, right?
No, that's not the definition of
Oh,
an atlas. Not every open set needs to be mapped by a chart.
Just a cover of.
Yeah,
It's not a cover.
it's just a cover. Every point has to have a neighborhood chart.
I see.
And right, also the same set can have multiple charts, right?
Yes, of course. You can have overlapping charts. That's not really a problem, right? So an atlas is a family, like I would say, a family of maps, right? Maps that are your charts, and then a union of such two sets is again a set, and you have many maps inside these sets, and you have to check for them to be compatible that that the transition maps in question are diffeomorphisms, right? Okay, so this is like how we depict it, right? One is a notion of an abstract manifold, an abstract smooth manifold, and the other is the usual Euclidean line. Okay, so and the usual Euclidean line is where all the stuff is done, right? The abstract manifold serves as a kind of a framework for us to consider all of these weird structures and all of this weird stuff, abstract stuff. Okay, So a transition map is nothing else but the map that goes like this, right? So this is what it means to be a transition map. So I'm not sure how I am going to write this, maybe as such. So, and this, in our case, it would be nothing else but phi of IDR to the power of -1. So what do we need to check in this part of this exercise is that, I mean, this is what we are asking ourselves, is phi of IDR, and now this is a very silly way of writing, of course, identity on R to the power of -1. This is nothing else but identity on R again, right? And identity composed with anything is that anything. So this is like really silly. But I'm nevertheless going to write it. So is this map a diffeomorphism? In the usual sense. i.e., is it a smooth map with a smooth inverse? Okay, so this is the question that we are trying to answer, and many of you are eager to respond. So what is the answer?
The answer is yes, because phi is a diffeomorphism. We can just cross out the identity because it does nothing.
Okay, let's first of all, let's write phi of IDR to the power of -1 is equal to phi. So this is this is a map, x maps to x to the power of 3. So what is its inverse?
The third root of x.
Okay, so all right. Did you change your answer now that you see that you have the third root of x?
No, I don't.
Why not?
Well,
Is third root of x a smooth function in the usual sense? What is its derivative at 0?
no. Infinity.
Yes, exactly. So the slope of the function third root of x is a vertical line, right? So I mean, the more rigorous argument would be that that the function x to the power of 3, the derivative of this function at 0 is equal to 0, right? So that if this map would be invertible by inverse map or function theorem, you would have 1 over 0 is the derivative of the inverse of this map, which is the third root, right? So I'm sorry. The slope of x maps to third root of x is a vertical line. I'm not sure how to say this in a better way. it's differential. So at 0, right? And now I'm building up parentheses here. Okay, so the slope of this map is a vertical line at 0. So this means that its differential at 0 is infinity, right? So the function x maps to third root of x isn't smooth at 0, right? So this answers our question. Okay, phi is not a diffeomorphism in the usual sense. And hence, the two smooth atlases aren't compatible.
So two atlases are compatible if and only if they're diffeomorphic between each other.
No, we will see in the B part that these two smooth structures are, I mean, these two manifolds endowed with these smooth structures are diffeomorphic. Okay, so what does it mean for a map to be like a diffeomorphism between two smooth manifolds? How do we define a diffeomorphism of two abstract manifolds?
Via topology, so that maps open sets to open sets.
Okay, that's going to be a little too little. So
We compose it with charts.
okay, yeah, that's more or less everything we've got. We have to compose it with charts and check that locally. So in these charts, a certain map is a diffeomorphism or a smooth map in the usual sense, right? So what we're going to do is we are going to first maybe draw a picture of some sort, okay? And this picture would be something like this, R, and let's write it in this way. Here, I am denoting this pair, right? This R and IDR. This only means that I am endowing my abstract manifold R with the usual smooth structure, which is just given by the identity, right? And the second one on the right-hand side, this would mean that I am trying, that I am, how do I say this? That my codomain is an abstract manifold that is endowed with the smooth atlas given by phi, right? Okay, so yeah, I am searching for what kind of a map. So here I have like these charts, right? IDR and phi. So, and this goes to R and this goes to R. So the question is, is there a map phi such that, and now we have to make this whole composition, okay? Such that, so big phi of ID R to the power of -1, which is a map from R to R, is a diffeomorphism in the usual sense. So this is our question, right?
Wouldn't big phi just be the square root of 3? I'm the cubed root.
Exactly. So define phi of, so phi goes from R into R as a map between sets, right? But as a map between smooth manifolds, it goes from like it's written above. Define phi as said as the cubic root of X. So then we have big phi of ID R to the power of -1 of X is equal to phi of big phi of X, and this is now, so this is nothing else but phi of third root of X, and this is third root of X to the power of 3, which is again X. So this means that phi of IDR to the power of -1 is equal to the identity map on R. Which is, of course, a diffeomorphism in the usual sense. Okay. So this means that the two smooth manifolds are diffeomorphic. So this is to display the abstractness, the abstract nature of smooth structures, right? So first of all, this may seem silly. It kind of is. So of course, just as in your favorite general topology class, you know, you could endow the real line with the standard topology, or you could endow it with, I don't know, a weird topology such as the topology of finite complements or anything like that. And then everything would behave in a weird way, right? And exactly the same may be said for these kinds of for smooth structures. It's a generalization of the of the notions that you are already familiar with, right? So in A part, these two atlases were not compatible because the transition map was not a diffeomorphism in the usual sense. It was the third root of x, right? And then in the second, I mean, the third root of x was where the problem was, right? And then in the second part of this exercise, this same function, which at first was not a diffeomorphism or is not a smooth function at zero, this same function helped us to get to a diffeomorphism between these two strange smooth atlases, or maybe the one with the phi is stranger, I would say. Okay, so yeah, this is to display somehow the abstractness of it all. Okay, so I see that we only have a minute until the break. So yeah, I wouldn't, I'm not too happy with long breaks. I want us to do as much as we can in our weekly 2 hours. So if that's okay, we only have like 5-minute breaks for all of us to get water and take a piss or anything like that. Is it okay with you if we have 5-minute breaks?
Yes, it's fine.
Okay.
Yes, it's okay.
Okay, so I'll see you in 5 minutes. Yeah, and let's now consider some very basic examples of smooth manifolds. Okay, so first of all, finite dimensional vector spaces. Okay, does anybody reckon how to endow it with a smooth structure?
The identity mapping.
Okay, but we need to. Okay, let's write over. Let's say F, which is from R or C. So you need to construct a homomorphism of some sort. And first you need to endow your vector space with a topology. How do we do all this? Okay, so first off, topology. What topology is like a natural one on the vector space V?
A topology induced by the Euclidean metric.
Okay, but now you don't necessarily have r to the power of n. So you don't necessarily have the Euclidean metric.
Mm.
Couldn't we just use, for example, the L1 or more basically any one of them because they're all equivalent?
Exactly. So we pick any norm. I'm not even going to denote it because we are not going to use it. So we pick any norm on V. So one should, of course, have the conception of what a norm on a vector space is. So we pick a norm. And then since V is finite dimensional, any two norms are topologically equivalent. So this means nothing else but the fact that they give birth to the same open sets. Okay, so I don't know, the open balls, whichever norm you take is going to be equivalent to any other norm you take. And of course, norms exist on vector spaces, right? You may, for example, I don't know, pick a basis on V. So you may identify it indeed with the Euclidean space, let's say R to the power of n, and then you may pick the standard Euclidean norm, as Mikhail Pachnik said, and you may like somehow via this isomorphism between the vector spaces, you may I'm not sure how to say this. You just take your norm back to your vector space V. Okay, that would be an example of one norm on your vector space. Okay, this would mean actually that you are promoting your isomorphism of vector spaces to an isometry, right? So yeah, and this is what gives us the topology on V. Okay, so that's the first thing. The second thing is the smooth atlas. So how do we endow V with a smooth atlas?
We could, for example, fix a base of V and then just map each component.
Exactly. So let Vi, I goes from 1 to n, be a basis. Okay, and what Matej said is that we construct a global chart is given by mapping, so Vi into the standard Euclidean basis vector, right? This would mean the standard one, the one is in the ith place. This is in f to the power of n. And extending by linearity. So what this means more or less is we have so any vector V may be written as so sum from 1 to n, and I'm going to write now xi of V. These are like components. These xi of V are nothing else but numbers that are like the factors in expansion of a vector V with respect to the basis Vi. Okay, so we take such an expression and we map it to the vector xi of V ei. Okay, this would mean that we are extending by linearity. Okay, and of course, this is a global chart since it covers the whole V, right?
Does the x to the power of I mean actually the exponential function, or
this is just x does not mean a thing in this exercise here right now. So this is nothing else but a number. Okay, this xi of V is my like my way of denoting the numbers in the expansion. Okay. So yeah, okay. So why is this a homomorphism?
Because it's a linear function.
Okay, so yeah, here we need maybe yeah, the argument from functional analysis that says that any linear map from a finite dimensional space to an arbitrary normed space is continuous. Okay, so any linear map from a finite dimensional vector space to a normed space is continuous. So this now implies that the above map is a homomorphism. With respect to the to any norm, so with respect to the topology that we endowed on our space. So okay, let's try to consider what happens if we pick another basis. Does anybody reckon what happens if we choose another basis, like not VI, but WI?
Maybe things are the same if we choose another basis.
Okay.
I don't see why they would be different.
Yes, but that means we have like an additional chart. So the question, my question for you would be, is the transition map between these two charts a diffeomorphism?
Yes, because we can use a linear combination of vectors from one basis to write the vectors of the other space.
Okay.
The basis vectors.
A more concise way of saying this would be that we have the transition matrix between the two bases, right? Which means that we may go from one basis to another by using an invertible matrix. Okay, so and yeah, maybe let's write these things down. So another choice of a basis of V gives us a compatible chart on V. Oops. Since the transition map between the two charts is the invertible matrix that corresponds to the transition matrix. Yeah, between the two bases. Okay, and you may maybe write more stuff down if you really want to. I'm not going to. So this is hence diffeomorphism, right? Okay, that was the first example. Let's proceed. Let U be an open subset of R to the power of M, and let F from U into Rm be a continuous function map between this open subset and the Euclidean space R to the power of M. Okay, and some of you may know what's approaching. We define the graph of the function f as the set of all pairs x f of x from x is from U. Okay, so this is now a subspace of U times R to the power of M. Okay. So for topology, we really have no choice, right? We just take the subspace topology. So the regular one, okay. Okay, so what about the charts? I'm sure you know it.
You can just use projections.
Yes, exactly. So smooth structure. We take the projection on U of this graph. So this is nothing else but the map PRU x f of x maps to x, right? Okay, and this is again a global chart. On the graph. So is this a smooth manifold? Does anybody reckon?
Yes, it is. Is that right? Is a projection a smooth mapping?
Okay. So first of all, let's discuss whether this projection is a homomorphism. So I said it here, it's a global chart. This immediately implies that the projection is a homomorphism. What is its inverse?
X dot f of the x comma f of x. And
X comma f of x, yeah.
yeah, and f is continuous.
Yes, exactly. So so f is continuous, hence x maps to x comma f of x is continuous. So this is the which is just the inverse of PRU, right? Okay. Well, what about smoothness?
Isn't smoothness just continuity? Did I misunderstand something?
Yeah, well, smoothness, the additional assumption to a topological manifold, for it to be a smooth manifold, is that the transition maps are smooth, right?
Oh.
So here we only have one chart, right? And the transition map of a chart to itself is just the identity map. So this is actually a smooth manifold in the abstract sense, right? Even if f is not a smooth function. So this is an abstract smooth manifold, even if f isn't smooth. Okay, but one should note that this is not a smooth submanifold of Rn times Rm, right? It's a smooth manifold in the abstract sense, but it is not a smooth manifold in the sense of a smooth submanifold of the Euclidean space. So let's write here. Note that is not. Note that the graph is not a smooth submanifold of U times Rm if the function or the map, maybe, if the map f isn't smooth. Okay, we may maybe have a counter example. That's just the maybe the most obvious one would be something like this. So we have the graph of the absolute value. Okay, and as a submanifold, this is the problem, right? This cusp here would prevent this space from being a smooth submanifold. This is like just hand wavy explanation. So this cusp here would prevent this set to be a smooth submanifold in R2, right? But as an abstract manifold, it is smooth, okay? Because it only has one chart. So one may pose the question, what are, for example, smooth maps? So we will get eventually to the notion of a smooth map, but for those who maybe have already have had the course of analysis in manifolds for you to contemplate. So what are smooth maps on, let's write maybe on graph of apps. And furthermore, what is the tangent space at the point 0, 0. So these are certain notions that we are not really familiar with yet in this course, but some of you are already prepared to contemplate such questions, right? So, and the answer would be that smooth maps on this abstract manifold must be such that they smooth the cusp out in a way. Okay, you may write down the definitions and see for yourself. Okay, so the next one is really simple. So let M be a smooth manifold. And U an open subset of M. So then U automatically comes with a natural structure of a smooth manifold, right? We just endow it with the subspace topology. And what about the charts? How do we get the charts here? So let's say that UI phi I let's say that this is an atlas, a smooth one on M. How do we get to the smooth atlas on U?
Just make intersections.
Yes.
Oh.
Intersections and restrictions. So UI cap U I still runs in this index set. So this is a smooth atlas on U. And I'm not even gonna go ahead and check anything because everything is really clear here. UI cap U is an open subset of U, since both of these sets are open, and with respect to the subspace topology, phi I restricted to an open set is again a homomorphism. Of course, we have to keep in mind what the codomain is. Now we have to also restrict the codomain, right? So we have that, and then we have the transition maps, and the since we are doing nothing else but just restricting to open subsets, diffeomorphisms stay diffeomorphisms, and that's more or less it. So we are not going to bother with this. Okay. Next example. For those who had analysis on manifolds in the previous semester, that this will be really clear. So let F be from either the real numbers or the complex numbers, and let N be a natural number. Then we have the set GL N F. Oh, and usually we don't write the semicolon here, we just write a comma. Okay. So these are matrices, N times M, which are invertible. So how do we naturally endow this set with a smooth structure? Now, those who haven't contemplated, who have already contemplated this question, please spare some for your colleagues. Anyone?
What's the question?
So how do we naturally endow this set with a smooth structure?
Meaning charts.
Sorry?
Meaning charts for every. Oh,
Yeah, more or less.
determinant, maybe?
Okay. What about the determinant?
So basically, we have to map this space to an R to the power of n space with the mapping.
So yeah, more or less, but there's a really easy answer to this that does not require any meddling with charts or the topology or anything like that.
Couldn't be the identity, right?
Yeah, well, the identity won't do it. The determinant map, the answer lies in the determinant map, but what do we do with it?
Couldn't we just take the pre-image of zero, the complement of zero?
Exactly. So GL and F is nothing else but the pre-image of the determinant of this set. Okay, so the determinant goes from the set of all n times n real or complex matrices. It goes to F, right? And this is not only a continuous map, it's a polynomial, hence it is an analytic map. Polynomial. Hence, I'm just going to say continuous. Okay. So, and the determinant is continuous. F minus 0 is an open set. So this means that this thing here is open in the set F n times n. Okay. So now use E over C. Okay, and so that I won't bore those who've already had this course, can we say anything about connectedness? Does anybody have an idea?
I would guess that it's not connected because there's a discontinuity at 0.
Okay, there's not a discontinuity. There's just like a missing point. That's
So it
what
is
I
connected.
wanted to say, probably, right?
Yeah, I meant to say the opposite, actually. Thank you.
Yeah, I mean it's difficult to put in words sometimes. Whoa, sorry. Yeah, especially in the context of these topology and smooth manifolds and stuff. It's sometimes it's difficult to put this in words. But so, what do you think is the general linear group? So this one, GL and R, going to be connected. So let's consider F equal to R. So that's what Mikhail probably had in mind when he said that at 0 there is going to be an issue.
So basically the question is if we can't go smoothly from positive numbers to negative ones.
Yes, more or less, more or less. But the question is even simpler when you don't consider path connectedness, but only connectedness. Because you just wanted, just now you wanted like to make a path from the set of those matrices that have positive determinant to those who have negative determinant, right?
Yes.
Okay, but now try to consider.
But we don't have zero, so we have two lines that aren't connected.
Okay, so the pre-image of determinant or via the determinant of the set 0 infinity and the pre-image of minus infinity to 0, these are open disjoint non-zero sets.
Non-empty sets. Probably.
Non-empty, yeah. Non-empty sets whose union is GL and R. Okay, so GL and R isn't connected. Okay, well, how about F equals to C?
It is connected.
Yes. So GL and C is connected. So, and this is the reason why any complex manifold is, drum roll, what do we have? Any complex manifold, so
It's connected.
is what?
Connected.
No, because I can take always the joint union of two complex manifolds.
Smooth.
No, I mean, smoothness is automatic. Like, what does it mean for a manifold to be complex? It's nothing else but that the transition maps must be holomorphic, right? Not only smooth, but holomorphic, analytic, okay? So, and does anybody have an idea what I am going to write here now? It starts with an O.
Orthogonal.
Okay, now you're just guessing. Try to think. Or guess.
Open.
Yeah, that won't do it. Any other contenders?
Well, what would connectedness even imply?
Yeah, say, well, that's the question. Why would connectedness of this group imply anything on any complex manifold?
Maybe something about treating it as a vector space.
close. Maybe. Okay, so let's try to do this bottom up. Well, you have, like, let's say that you have two charts on your real manifold, right? You have two overlapping charts. So then you have the transition map, okay? And let's say that the overlap of these two charts, so the intersection of the open sets, let's say that this is connected, okay? Let's say that this set, sorry?
Orientable.
Yes. Orientable. So if I were to continue my my thought process, I would think in these terms, right? So I have an open subset on which two charts overlap, right? And this, I am assuming that it is connected. Now, if I take a look at the Jacobian of the transition matrix, it may have a positive or a negative determinant, right? Because I am assuming that this intersection is connected. Okay, so if it is positive, okay, then these two charts are said to be, so defined to be of the same orientation. Okay, so we say that they determine the same orientation. And if this may be consistently done through all of the so for all of the charts, if we may do this consistently, so if we may choose such charts that these transition matrices are at every point that their determinant is of the same sign, right? Then we say that our manifold is orientable. Well, in the case where we have a complex manifold, these transition matrices, this Jacobian will be a complex matrix, right? A matrix with complex entries. So, but since this GL and C is connected, we have no other choice but for the manifold to automatically be orientable. There is no other notion that we can work with than these. Okay, so that's something that you may contemplate about. Okay, so we have 15 minutes left. Let's consider spheres. So let n be a natural number. We could also assume that it is 0, but that case is trivial, so I'm not even gonna bother with it. So Sn is defined as the set of all such numbers from Rn plus 1 such that x1 squared plus dots plus xn plus 1 squared is equal to 1. Okay, so this is the unit sphere. Okay, so automatically we have a topology on this set because it is a subset of Rn plus 1, right? So it is the subspace topology. Okay, well, I'm not even going to write that we are endowing Sn with the subspace topology, but let us consider smooth structures. Okay, so various smooth structures. And the first one will be defined just by, this is the most natural one. This is where we consider the sphere locally to be a graph of some function. Okay, so let me first write and write these sets, and then I'm going to draw some pictures for you to like grasp this intuitively. So let's define the set UK plus minus to be the set of all such so vectors, or whatever you want to say, from Sn, such that plus minus xk is greater than 0. Okay, so what this means is, for example, let's consider S2, right? We have U3 plus is equal to, and now I'm gonna have to draw some stuff here. So this is a sphere, right? And this U3 plus is nothing else but the upper hemisphere without the equator. Okay, so U3 minus would be the hemisphere below, and you also have the left and the right one, and the front and the back one, right? So there's 6 of them. Okay, and not only that, we have to, of course, define charts. So, and we have to define them for every k. So k is, so maybe I should write here, k is from 1 to n plus 1. Okay, so we define these charts as projections. So this is commonly denoted as with a hat. Okay, and what we mean by this is x1 and then xk minus 1, xk plus 1. So we are leaving the kth component out, right? Okay. So that now phi k plus minus is a map from uk plus minus. Okay, if I am picking a plus with the phi, I am also picking the plus with the uk. Okay, and this goes into the open unit n ball. Okay, so this is commonly denoted as such. Do we know what an open unit n ball is?
Yes.
Or would you like me to write down the set? Okay, we all know what it is. So, well, of course, this map is continuous. It's like just missing one component. But now, in order for us to make sure that it is a chart, we have to like check that its inverse is also continuous. And how do we do this? Well, look, this is really trivial because this was a projection. So now we're actually dealing with the case B, where we had the graph, right? The graph of a continuous function. So that so phi k plus minus inverse of x1 to xn now is nothing else but x1, and then we arrive to the k minus 1 place, and now we have to, of course, have the prescription of like of how to I'm not sure how to say this, but it's nothing but a graph, right? So this would mean 1 minus and norm of x, right? And squared. So this is nothing else but I runs from 1 to n xi squared, right? Okay, and then furthermore, we have xk plus 1 and x n plus 1. Okay, so this is like its inverse, and obviously
It would just be xn, I think, because we don't have xn plus
yeah,
1.
of course, xn. Just the xn. Okay, so these are obviously continuous, right? So they constitute charts for a topological manifold, and now we have to check the smoothness criterion, which means that we have to check the transition maps. Okay. Oops. So the transition maps are a little bit more trickier, but not all that much. Let's just write them down for I less than j. Okay, and let's have phi I plus minus of phi j plus minus inverse. Okay, let's just try to write these down. Okay, and it is really straightforward. It's just now, since I is less than j, we would have that the xi here is missing, and then we arrive to xj, which is this one.
Can I just ask something?
Yes.
The way we define the inverse, how many components does the image of the inverse have in this case? Because like we wrote, doesn't it mean that it has one component less than the dimension?
Yes, you are completely right, and I am mistaken here. So this one must be without the +1. I am sorry. So yeah, in the kth place, we insert the prescription of like the so-called graph, and then we continue, right? So you should definitely erase the k plus 1, the +1 part.
So also in the case where the last line you wrote,
Yes.
it's also not.
Also here. Okay. And now this is obviously a diffeomorphism, right? In the usual sense. Okay, so this is one possibility of defining charts. We also have another way of defining charts. Now, note that so before we make the next like definition of charts, here we have 2 times n plus 1 charts, right? And in many cases, it is better to have like the least amount of charts possible. Okay, so another possibility stereographic projection. So now we have two charts only, and this is Sn without the north pole. This goes into Rn, and it is defined in the following way: x1 to xn plus 1. And so this is like from the intuitive argument from your analysis 2 course. So there's a nice derivation of this formula of the stereographic projection, which we are not going to do, obviously. And we plug here x1 and xn. So the inverse of this is phi plus to the power of -1. So this is really straightforward to check. We are not going to do it. So we have this in the denominator, and now we have 2x1, 2xn, and x normed squared -1. So, and both of these are continuous, right? So this would mean that we now have achieved like the we arrived to the chart for the n sphere without just one point. So taking one point out, yeah, we may obtain a chart, right? So the other chart would be where we just remove the south pole, okay? So that would be phi minus Sn minus the south pole. And this isn't just r, this is r to the power of n, obviously. And we define this as in the following sense. So this is defined with the help of the stereographic projection defined above. And we have its inverse is given by phi minus inverse is just equal again to the inverse of sigma plus. And now again, first take the like the opposite value of the argument and then the opposite value of the whole expression. Okay, so it turns out that the stereographic projection without the south pole is of this form. Okay, so before we conclude this exercise session, let us maybe just compute the transition maps. And the transition maps would be, for example, we could take a look at this one. Okay. So this is, first of all, nothing else but sigma plus of minus sigma plus inverse minus x, right? This is by definition of the inverse of the sigma minus. Okay, so, and by the definition of sigma plus inverse, this is nothing else but the following expression. So this is really straightforward to check. Now I'm not going to reason right now regarding this. Now this is just a matter of plugging the minuses inside your expressions, and it's like a really vain excuse for a procedure. Okay, so this is what we get when plugging in the minus x and taking the minus of the whole expression. And then in the end, what we get is here 1 minus norm x squared, 1 plus norm x squared. So this is just by using the definitions. I'm not doing anything really here. X squared plus 1 and x1 dots xn. Okay, but this is now nothing else but 1 over x squared x1 to xn. So, and note that that this composition should be so checked for any x that is different from 0, right? So this is a for all x that are different from the 0 vector in Rn. Okay, and that is precisely where the transition map should be checked. So one may so I'm gonna write here homework, fill in the details. Regarding where so regarding what is the okay. So yeah, we are ending this exercise session. Maybe just one more small note is that it is trivial, or let's say easy, well, to see that the above atlases are compatible. So this is also maybe for your homework to contemplate on whether the transition matrices of the with respect to the charts given in the first case and then via the stereographic projections, that these are diffeomorphisms, right? Okay, are there any questions?
Yes, when you say diffeomorphism in the usual sense, is there an unusual sense in which a thing can be a diffeomorphism?
Yes, the diffeomorphism in the abstract sense of smooth manifolds, right? So as we saw in like the first exercise, the diffeomorphism between like a real line with the standard structure and the real line with a maybe more unintuitive structure was given by the third root of x, right? And this is not a diffeomorphism in the usual sense. Okay, so it's not a diffeomorphism between R and R that have both the standard smooth structure, right?
I see.
That would be my answer.
Jaz bi imel še eno vprašanje.
Aha.
Profesor je na predavanjih omenil, da bomo na koncu leta imeli neko predstavitev ali neke, ne vem, prezentacije, nekaj takega, pa
Ja.
da bi mogoče zven to pogovoril, pa če lahko malo vi bolj podrobno poveste, kaj je bilo s tem točno mišljeno.
Ja, s tem je bilo mišljeno, da torej pač vi opazujete, so maybe I should answer in English. So regarding the final like presentation or whatever of your like sort of an essay that you are required to write for the for this part, right? For the exercise sessions part. So you are invited to like explore different theoretical possibilities of differential geometry, and in the end to write your own essay regarding it. So you should like this is on you, right? This is for you to explore what interests you in the domain of differential geometry. I mean, we are going to like we're going to meet a lot of new concepts here, and there are some concepts which I reckon that you will find interesting. So this is to invite you to further explore these concepts that you will find interesting, right? So that's more or less the point of this essay. So does that answer your question?
Ja, pol če razumem, cirka seminar, predstavitev tako.
Tako.
Hvala.
Any other questions?
Maybe I have a question.
Yeah.
So this is more general, I guess. Let's say in general relativity, we always have, I mean, we often have situations where there are various discontinuities. Let's say you have your tensor that describes the matter content of the universe, and then, you know, when you have Earth, at the surface of Earth, there's a discontinuity. So we kind of talk a lot about smooth manifolds, but then it seems like we like to use non-smooth structures that are still kind of relatively regular. I mean, you know, having a step discontinuity isn't exactly drastic. So like, is there some more general theory that encompasses this? It takes this into account?
You should note at all points that, I mean, at all times that even though we're in the smooth category, we are also in the topological category. So nonetheless, if your objects aren't smooth and are only continuous, you should anyway be able to contemplate like regarding, I don't know, their continuity or anything like that.
How about something like, you know, distributions on manifolds? Because that would also sound useful. So have like something like a point or some distribution.
Like a Dirac delta on a manifold. Yeah, well, I mean, those kinds of concepts are really evasive, yeah, and you have to be really careful with them. But usually they are, I mean, the Dirac delta is, as you know, that's not a function, right? It's not even a map. It's like it's a distribution, and as such, it is functional on the set of like tamed functions, right? So, and you may consider these on a manifold. Okay, so that's not really an issue. You may consider functions on a manifold, and you may consider their functionals, right? So, just like derivations.
Yeah, okay.
So, I mean, there's, yeah, I'm not sure if I have a better explanation regarding this, but in any way, we want to deal with with smooth structures and with like covariant derivatives and so forth on smooth manifolds. This is like the central theme, for example, of general relativity. Okay, and note that whenever you are like exploring concepts such as black holes or anything like that, like in the center where there is a supposed singularity, right, the infinite density of an object or whatever you want to call it, that's not a part of your space-time. That's you cannot describe things. You can describe things beyond event horizon, so inside the black hole, but you cannot describe it at the singularity where the mass is supposedly like squeezed in.
Yeah,
So
that's why I was asking about Dirac deltas, because
yeah,
you could maybe extend it somehow in there to add a point that has the singular behavior.
yeah, that's a very interesting thing to debate around, but I'm not sure that we are going to get anywhere. I don't know that I don't know enough about such stuff. I have seen black holes like in at least in my notebook, but yeah, I haven't contemplated such stuff. Maybe we should have like another sessions for such debates because they seem interesting.
Thanks.
Okay, so let's conclude this exercise session. I'll see you next Friday.
Bye.
Goodbye.